Thank you, Chong. Good afternoon, everybody, or morning, depending on where you're joining from. My name is Jeremias Sulam, and I'm an assistant professor at Johns Hopkins University, and I'll be the moderator for the last section of today's workshop, which is going to be a panel discussion. So I'm actually very much looking forward to this. We have a very nice selection of experts who will be joining me in the discussion. We will be having Professor Rene Vidal from Johns Hopkins as well, Yuejie, who you just heard from CMU, as well as Professor Tom Goldstein from UMD. And to represent a younger voice and opinion on some of the questions we're going to be exploring will be Armbar, who's a PhD student in the computer science department at Johns Hopkins University as well. So welcome to all of the panelists, and I'm very excited to have you here to gain some insights in your opinions and your takes on some of the questions that we are discussing here in the workshop. So maybe let me begin by perhaps, let's say, one of the most standard questions, but I think that is very much of relevance for everybody here. Which is, what do you think is the biggest open problem in deep learning research today? And feel free to go and take a shot at that question if you'd like, and mute yourselves.
All right, I'm going to say something about this because it's kind of a big question. I think so a mainstream answer to that would just be generalization, right? We don't understand generalization in neural nets, but I think that's just too big of a can of worms to open. And so maybe to nail down something a little bit more specific, I might ask something like, what are the implicit biases of optimizers? And not necessarily specifically stochastic gradient descent. But I think the implicit bias of optimizers is really a thing that we don't understand at all. And I think we have studies that try to understand what you might call implicit regularization of SGD in very idealized situations. But I'm not sure that the theory that we have really describes the kind of behaviors that are important to generalization. Especially when you consider the fact that so one of the things I'll talk about when we talk tomorrow is I don't think generalization actually depends very much on the optimizer. You can get good generalization properties with all sorts of different optimizers, even non-stochastic optimizers. You can use
let me poke a little bit more on that. So you're saying it doesn't depend on the optimizer, even in over-parameterized models?
I don't think there's a very strong dependence on the optimizer. Like as an example, there are papers that train SGD with batch sizes of 64,000, and they get great results, right? There are methods that train neural nets using LBFGS, so methods that use Hessian-Free methods and sequential quadratic programming. In my group, we had a paper that does ADMM. There's a great method called proxprop that does alternating least squares, and all of these methods converge and get great generalization. And now there's small differences between them, right? Like maybe for a classification problem, Atom will come in 1% worse than SGD. But all of these methods generalize really well when you consider the fact that a random guess on ImageNet is 0.1% accuracy, and a really good optimizer can get, you say, 96% top 5 accuracy, and then a garbage optimizer might get 93% accuracy, right? We're always fighting over these tiny little differences in generalization that we can get. And I think the reason why is because you get a huge generalization boost for free no matter what optimizer you use. And so the only thing left to fight over is the stuff that not everybody gets for free. And so we quibble over these, plus or minus a few percentage accuracy points you get depending on whether you use Atom or SGD or what batch size you use or whatever. But I don't think that we understand most of the generalization that we're getting. I think that focusing specifically on SGD and stochastic regularization might be a little bit of a red herring.
Thank you so much, Tom. do any of the other panelists want to comment?
Feel free to totally disagree with me or comment on something different entirely.
I would say that I wouldn't say that there is a single most important problem in modern deep learning, but rather there are many that I think are very cool and very interesting to be understood. I certainly agree with Tom that the question of generalization and the interplay between optimization and generalization is one. I would add perhaps that the learning dynamics and the role that data plays in that dynamics, and I think we saw a little bit from the first talk this afternoon, the question of if the labels are noisy and in what order do I present the data and how that affects generalization. So I think that's really a very interesting area. The question of generative models, I think many of us working in vision and generative models for vision for a long time, we were always never getting anything that would generate good looking images. And the fact that that's possible today, it's first of all very surprising, but at the same time, we are very far from understanding why that is working. I'm very curious to understand what the training objective for GANs, what kinds of distributions they can learn. Why is it the case that if I change the criteria from a maximum likelihood, which is whatever we were used to the current adversarial criteria, why it makes such a difference? Then what can be learned, actually. I don't think there is any theoretical result saying that I can even be guaranteed to learn a mixture of Gaussians with GANs either. So I think that would be a second. A third topic, I think, is the integration of deep learning models with physics-based models. I think that data-driven is great, and that's what we all do when we do deep learning. But inevitably, it's why should I completely throw to the garbage the knowledge I have about concrete physical processes? And my thinking has always been that the models we use are always approximate, and that we should be able to use those models for maybe the quote unquote almost linear regime, but we should be able to use deep networks and data-driven approaches to model the unmodeled parts, if you wish. Let me just stop there. That's already three different areas that are dramatically different. So
That's excellent. Thank you, Rene. And so perhaps this connects very well with my next question, which is, what do you think is the most important practical benefit of low-dimensional representations in deep learning, which is basically the theme of this workshop? Or in other words, why would industry be interested in the topics of low dimensionality in deep learning?
Yeah, low dimensionality is such a broad concept that that's difficult, I think. Low dimensionality is just such a broad concept, right? And I think today we've seen it in a lot of different forms, right? Like low dimensional feature representations, kind of like low rank factorizations of matrices. I guess, in some sense, low dimensionality kind of makes things interpretable. It's just difficult for people to wrap their brains around things that live in extremely high dimensions. One of the nice things about things like matrix factorization models is that they are interpretable, right?
So if I can also drop an idea, when I read in the same sentence the words low dimensionality and industry, the first thing that comes to my mind is the Netflix challenge, which I think was one of those broadly spread challenges that really showcase, I think, what low dimensionality has to offer, how much benefit you can extract when you know that your data actually lives in a lower dimensional subspace. Now, this Netflix challenge was something that a lot of people have been working on now by 10 years, or perhaps even more. And so when thinking about this, I was trying to come up with, okay, what could be the next sort of challenge that would really come and showcase what leveraging this low dimensionality of data has to offer, but now taken to the year 2020.
Actually, the Netflix challenge is an interesting example, because that is a space where deep learning hasn't necessarily had the same kind of huge, like, recommender systems. There are deep learning based recommender systems, but I don't think that it's had the same huge impact that it has in other spaces where data is more structured. Yeah, but just, I guess, like, looking at low dimensionality. One challenge I was actually going to mention related to the last question, just like what are the big challenges, is that it's really difficult to apply deep learning effectively when we don't have really structured data. So, like, for language or audio, like speech or vision, images, we can exploit basically convolutional structure or something very similar to convolutional structure in order to get great results. And these sorts of invariances seem to make deep learning really powerful because we can exploit those invariances. For problems where we don't have that sort of structure, deep learning doesn't seem to be super successful. So if you look at, I don't know, like Kaggle type competitions or like the UCI data sets, very often the state-of-the-art systems for those problems aren't deep learning based, because they're just, you have unstructured features for that represent objects. It's not really possible to build. There's not enough invariances to be exploited that deep learning seems to really be a smashing success over just conventional things like random forests and linear classifiers. But I think Netflix is an interesting problem, because it almost sort of falls into this category. When we don't have all sorts of structure and invariances to the features that represent objects, deep learning doesn't seem to be a big win. And instead, we seem to be better off just looking at low dimensional representations, because they're just more interpretable, and it's easy for us to sort of hand construct solutions to these problems when there's not enough structure to be worth learning the features from the data.
I think unstructured data is really something very important that industry people really care about. So when I talk to my friends, for instance, in companies that deal with large amount of textual data that they scrape from the internet or they have on their website, they often find these large streams of text that people post, and they have to parse these large streams of text. And often these data streams are very noisy, and it really matters to them that they can process these streams and get to a low dimensional representation that they can really interpret. And at the end of the day, they end up using these simple models like random forests or even just linear SVMs, things like that, just because they're more interpretable. So I think interpretability is a very important aspect for which low dimensional representations are interesting should be interesting to the industry.
One other related area that I would mention is actually graph neural nets. I think this is maybe related to some of the problems that you're mentioning that arise in industry. But graph problems are very common in industrial settings. And that's another setting where neural nets aren't necessarily a smash hit. There's been kind of literature kind of bounces back and forth on how successful graph neural nets are. And I think recently there's been a few papers that came out, claiming that sort of scaling things back and using more conventional classifiers that don't have as many learned parameters as actually performs at least as well as graph neural nets for some applications. But yeah, there's a lot of these industrial problems where low dimensionality and interpretability seems to win at the end of the day.
I think classically people study low-dimensional structures, particularly for inverse problems, because of sample efficiency, right? We often talk about we have underdetermined problems, so that we need to impose certain low-dimensional structures. This seems to be sort of quite different from deep learning perspective, right? Where you often say you have a lot more data and you throw in a lot more parameters to fit. But on the other end, deep networks are also trying to search for some sort of low-dimensional structures, right? After all, you are sort of doing some of this function approximation. So at the end of the day, maybe it is indeed find some low-dimensional structure in the data, but through using a very complex over-parameterization, rather than if I take my low-rank representation, it's actually a succinct low-dimensional representation for the low-rank manifold, right? I could also write down maybe another parameterization of my low-rank manifold, but using 1,000 more parameters. So maybe that's one of the differences between what we do in classical low-dimensional model versus this, modern low-dimensional model where you throw more parameters. Yeah, I feel like this low-dimensional modeling in this classical sense is more valuable, particularly for sample staffed problems. That we just don't have that amount of the training data to fit all those parameters.
I personally distinguish or split the question into two parts because I think there is value for low dimensionality in deep learning that has nothing to do with it being necessarily valuable for industry. So in particular, I think low dimensionality has a big role in understanding generalization. By and large, if you think about all generalization theory, at least in the classical setting, it always relies on some dimension. And it always, you get tighter generalization bounds when that dimension is better. A lot of generalization theory never relied on explicitly exploiting low dimensional structures in the data per se, other than maybe, there is some manifold there. The more recent generalization bounds that emerge from pack bias, they try to have some sort of prior, at least, that is built into the data. But I think really one aspect of generalization that I do think is essential is the match between the structure of the data and the structure and the design of the architecture for that data structure. And I would think that low dimensional structure is going to have a great role in deriving much tighter generalization bounds. It's going to have the role on designing accelerated algorithms that are particularly designed for exploiting those low dimensional structures. Going back now to the first question, what are big open problems? Architecture design, it's completely handcrafted today. And future architectures for new data modalities that are not just images or time series for which we know the structure and we know that convolutions are good, will require adequately exploiting those low dimensional structures. Now, the second part of the question is, are there relevant industrial problems, right? So low dimensional structure has typically been thrived in unsupervised learning, and deep learning has been primarily supervised insofar. And that might be a reason why we haven't seen a lot of great success of the exploitation of low dimensional structure in deep networks yet. But in moving forward, right, eventually, okay, this is an exaggeration, but all supervised problems will be solved, right? We saw 2012 to 2015 gazillion papers on solving yet another supervised learning problem with another 10% improvement. But eventually that's saturated. And so now there is a lot of research getting into, say, self-supervised learning and unsupervised learning. But we've not seen deep clustering or deep dimensionality reduction methods thrive as much as supervised methods have thrived yet. Variational autoencoders is one emerging area of low dimensional representations with deep models. But in terms of their applicability, I think they will thrive in applications where either I don't have enough data, and therefore there is a need for using some sort of unsupervised and self-supervised modeling. And another application that I think industry will care a lot is the ability to transfer deep learning models to new applications. And I think that's going to be critical, because I think, and we see that even also in the medical domain, right? A new problem comes, they're just going to have 100 patients, and I'm just never going to learn anew from that data. So I need to have the ability to transfer those representations to one problem, then to another, then to another. And in all cases, the data is going to be very limited. And so the interplay, the ability to train new models for new applications, the fine tuning by exploiting low dimensional structure, I think it's going to be what's going to potentially have the bigger impact. Let me stop.
Yes, actually, Rene, you raise a very, very interesting point, which I think I can try to summarize as follows. Traditionally, this low dimensionality or some sort of simplicity of representations has been enforced through the formalization of some signal model. Either your data was sparse, or it was low rank, or some other form of simplicity or effective low dimensionality. Now, deep learning, on the other hand, thrives, and these models tend to thrive when they are trained in a supervised manner. And so, very recently, there's this notion of self-supervised learning, like contrastive learning and some other techniques, which basically try to precisely deploy the regime in which deep learning excels, which is this supervised setting, but to solve problems that are unsupervised. And in fact, there have been, very, very impressive demonstrations of how this approach can learn representations that actually generalize very, very well. And then when coupled with only a small fraction of supervised data, they can perform as well or even better than the models that are trained entirely in a supervised manner. And so I think, to me and to others who work and who have worked on representation learning, where we often impose some prior on these representations, is that somewhat puzzling, right? And so my question is, how do you think that this whole theoretical background that we have on representation learning can be generalized to include now these representations that are being implicitly learned by these models? And perhaps the representations that are learned by GANs, by generative adversarial networks, may fall on that category, but I'm referring to specifically self-supervised learning and contrastive learning in particular. Maybe Atlas, who's one of the organizers of these workshops, can also pitch in. He has done some very interesting work along these lines as well.
Okay, thanks, Jerry. And actually, one of my most skills since attending every teleconference is to be queued suddenly by the moderator, because I could be away from the from computer from time to time. But luckily, I'm here this time. Okay, so maybe I can start to share some just a point to kick off this discussion. So I work on contrast learning and self-supervised learning a reason bit, and I totally agree with Jerry and all the previous discussion we just had that this pretty much remind how we were traditionally doing with extracting the low dimensional features and use that to extract features and then feed to the subsequent task. In the traditional pipeline, we do that in two stages. We design features from either prior experience or doing some unsupervised representation learning and feed to downstream tasks like we do in sparse coding and low rank representation. And in deep network, there was once a while people believe two stage now disappear, and now we are all converged to the one stage doing things from end to end. But I'm actually very happy to see within 2 years people start to realize the value of first do some kind of pre-training, do some kind of pre-training or some some kind of self-supervised learning, and then demonstrate those pre-trained features. Even they are trained in a task-agnostic way, they seem to be universally boost a wide range of tasks from the standard classification task to tasks which share substantially different prior knowledge, like detection or segmentation if we talk in computer vision context, and even in some drastically different tasks from standard generalization. For example, adversarial robust generalization. For example, I'm aware Tom's great work in adversarial robust transfer learning. We are very familiar with that light work. So yeah, so I think for that, there are several very interesting research questions I'm personally very interested to explore. I think the first so two main questions here, as we were asked in traditional two-stage feature design. First is, what priors or what invariance properties we actually try to capture in this data-driven self-supervised pre-training scheme. So when we talk about the pretext task, when we talk about the contrastive with certain kind of augmentations, what we're actually talking about. I think here we face a very much needed convergence of mathematical language when we describe a pretext. Because if you look at, for example, pretext or contrast, people describe it from more most works describe it from more intuitive computer vision language, like this is to inject translation invariance, rotation invariance, or maybe some removing some visual shortcut from the structure information. Those are all good, but I think that would be even more interesting if we could formalize that into a mathematical framework, like using group theory. And I think Professor Imar in the morning talk has introduced something very relevant as well, which actually I want to personally take a look at. So I think we still only have limited understanding here. Like I think for unsupervised feature learning, the most well-known principle is perhaps Infomax. And this year, Yonglong Tian and Philippa Sola's group has a very interesting paper called "What Makes a Good Contrastive Views." They also propose another aspect called InfoMean in contrast to Infomax, and saying the two actually should be considered together, like, about how to trade off between maximally preserving information from data and also maximally preserving information that are only meaningful to certain kind of variance we try to enforce. So I think more description from that aspect will be really helpful beyond just using computer vision's intuitive language to understand what a pretext or contrastive family are actually doing on. So I think that's one thing I'm interested, how to mathematically understand the self-supervision and contrastive task. There, well, I think in principle that definitely, for example, contrast learning definitely reveals some notions similar to local smoothness, continuity, and consistency. I think everybody will more or less agree on that. But I also think some great work, like I remember one from Julia Maria's group in I think that's from DeepMind, called Bootstrap Your Own Latent, a new supervised approach for self-supervised learning, some title similar to that, and showing some, I think that paper contains a very nice theory and a very nice potential theory that I personally like. So second question, so that's the first question. The second question I'm recently also interested in is, okay, so so when we use traditional feature design or two-stage learning, we're basically saying we first get the features. The feature have some property that we know that will display, and then we'll just use the features as a frozen representations and go ahead towards the downstream task. So, but in the pre-training and fine-tuning scheme, there's actually something very not very similar to that. That is, the feature once designed in the pre-training stage will further be tuned to adapt it to the specific downstream task. And I think there are a lot of mysteries in this fine-tuning step. For example, if you have learned a translation invariant feature, you have learned a robust feature that have a certain resilience within a sigma ball, then how much that property could be preserved in this fine-tuning process? And if yes, why? Actually, we like some work from our group, and I think some from Tom's group as well, investigated the robustness preservation in the transfer learning process as a specific context example. And I think at least our group's observation is robustness is actually very hard to preserve in the fine-tuning process. It will quickly decay and be forgotten if you don't specifically avoid that process. So here may make alert that even we have very good pre-training feature, don't take take it for granted that those prior and knowledge can be forever memorized and go all the downstream tasks you want them to do. Some will be more easily memorized than the other, and some will be forgotten. So I think that's another question that currently be less, I would say, be less sufficiently investigated in pre-training fine-tuning scheme. That is, even we can specify somehow intuitively or mathematically what prior knowledge we have obtained in pre-training, how much we could really pass on, how that is related to domain gap between pre-training and fine-tuning, how that is related to heterogeneity between pre-training surrogate task and fine-tuning target task. I think there are many open questions, and I don't believe I even know a slight portion of the answers. So sorry, I don't have more answers to share. I only have questions.
That's excellent. Maybe in another 2 years, we are going to have another workshop to discuss the answers that we've found, or some other people will have found to these questions. So actually,
good. Let's make it happen.
Yeah, absolutely. Let's make it a bet, and someone writes down these questions that Atlas was mentioning. So let me actually piggyback on some of your comments there, and perhaps ping pong a question back to Tom. So what do you think low dimensional representations have to offer in the context of adversarial robustness then?
That's a good question. Okay, first, I'm going to wind back a little bit just to say something. I thought everything Atlas said was really interesting, actually. There's a lot of good points. One thing I just think is interesting about self-supervised learning. Self-supervised learning is really just supervised transfer learning. Like you pick labels to put on your data and you train on that task supervised, and then you try to do transfer learning to another task, right? And so it's kind of like halfway between, sort of almost halfway between, conventional deep learning where the representations are completely learned, and then handcrafted features, right? You're sort of handcrafting the labels and then crafting them in such a way that the network should learn informative features, and then you're doing transfer learning. But to me, a big problem is just understanding transfer learning. When does it work? When does it not work? If you have two data distributions and you want to train on one and transfer to the other, how can we understand whether that transfer learning is going to be effective or not? And if you can understand transfer learning, then you could understand how to choose self-supervised tasks better. Because right now we just kind of throw a million different self-supervised tasks at a problem and just see which one works. But I think there's a lot of really interesting work to be done trying to understand transfer learning and self-supervised learning. Okay, wait. So where's your question? Low dimensionality.
Yes, and how they benefit, or how they may benefit either practically or theoretically adversarial robustness.
I'm not a big believer that dimensionality matters very much. Everyone likes to talk about how high dimensional images, like ImageNet images, are harder to defend than low dimensional images, like MNIST. We've done a little bit of work. Like we have this paper, our adversarial example is inevitable. It's just sort of like a theory paper where you look at a few issues. And one of them is we look at the theory of how the dimensionality of an image impacts robustness. And we have an experiment in there where what we do is we take MNIST images that are 28 by 28, and then we interpolate them all the way up to 128 by 128 and sizes in between. And then we just do adversarial training on those images. And what you find is that the adversarial robustness you get when the images are size 128 by 128 is exactly the same as the robustness you get when they are when they're 28 by 28, which is the original resolution. So I guess, what does that say about dimensionality? I guess what it says is like the extrinsic dimensionality of your data representations doesn't seem to matter very much, right? But I guess the simplicity of the underlying data manifolds does matter in some way, right?
That's right. That's actually what I was trying to get to. Not the ambient dimension of your data, but rather implicit low dimensional representations of the data that you have.
But I think there's something going on there that's different than, I think the reason why MNIST is so easy to defend, it's something a little bit simpler than dimensionality, right? You could have a very high dimensional manifold on one side of the cube, like one vertex of a cube, and then a very high dimensional manifold on the other side of the cube. And as long as there's an epsilon boundary between those two manifolds, you can create a robust classifier between them, right? And so there's something about that's difficult to characterize about the complexity of these data sets. I guess maybe it just has something to do with the margin between the manifolds that makes some of them easy to defend and some of them hard to defend. And I think whatever that is, it's not the same thing as dimensionality. It just has something to do with margin. What's interesting though, is that if you look at data sets like ImageNet, where you need really high dimensionality to represent them, it always seems to be the case that these kinds of image manifolds are all sort of tangled up, like all the image manifolds for different classes are sort of tangled up into each other. And it makes it really difficult to solve these kinds of robust optimization problems. So there is some sort of relationship between robustness and dimensionality, but it's a very complicated and not direct relationship.
I think recently there have been some works that try to exploit intrinsic low dimensionality of the data manifold to get better robustness guarantees. For instance, there was this series of works from, I think, Pranjal Awasthi's group at NYU, where they say that, okay, if you can model your data as a union of, or that you can model your data to lie on a low dimensional linear subspace, then a lot of these defense algorithms, for instance, projection to the low dimensional subspace or randomized smoothing to get certificates for your adversarial robustness, all of them seem to be certainly performing better. I think the basic intuition, basically is that you are reducing the degrees of freedom that the attacker has when they make a perturbation. I think, I'll talk a little bit about it tomorrow, but in some cases, if you assume a locally linear decision boundary, you can actually even show precisely what the optimal attack and the optimal defense is. But it's for a simple setting. But I think low dimensional representations have a important role to play when you look at adversarial robustness. But certainly, I agree that it has to be the intrinsic low dimensionality of the data and not what your ambient space looks like.
So I would perhaps derive as a corollary of what you just said that in order to make progress in adversarial robustness, actually what we need to make progress in is understanding these somewhat, in some sense, simple or low dimensional representations of data. Once we have these, then we'll be able to provide better guarantees, hopefully. Would you agree with that?
Right. In fact, even from the attacks setting, I think there were these works from EPFL and DeepMind by Fawzi et al. That looked at that if your underlying classifier or if your classifier has boundaries that look roughly linear, then your adversarial perturbations transfer across many of your images, and they showed these interesting results that that quantified how much your adversarial perturbations transfer across images when you have when the decision boundaries are very low dimensional of your underlying classifier. Whether it's a good thing or a bad thing, that's I think to be debated, but
Excellent, thank you. Any of the other panelists want to comment on adversarial robustness?
Yeah, I guess there are interesting results that are using low dimensionality to try to get robustness, but in some of those cases, I guess I'm worried. You can use low dimensionality results like to prove robustness, but I don't know if you can go some of those results don't go the other way, right? You can have very complex high dimensional manifolds and still have really robust classifiers.
Well, I can give you a very tight bound on the Netflix challenge.
That's true. Yeah. There are very good results from the Netflix challenge. Yeah, I guess. Yeah, there are certainly ways to model these problems. Using the things like linear decision model for multidimensionality. Well, how well some of those linear decision boundary models describe things like ImageNet, though, I'm not sure, right? And it's certainly the case that you can come up with very complicated high dimensional manifold problems that that have really wide margin decision boundaries and are still quite robust, right? But I agree with you. It is some of these low-dimensional models have shown, been able to shine some light on some of these issues in robustness, especially theoretical issues. But I still feel like dimensionality just isn't quite the end. It's like a small piece in a much bigger picture, I think. It's just my personal take.
Thank you, Tom. By the way, we also welcome questions from the audience. So if you have questions for the panelists, feel more than free to write them down in the chat. In the meantime, while that happens, let me change gears slightly and ask something a little bit more general. And that concerns the culture that surrounds modern machine learning research, which basically has driven some attention away from slower paced journal contributions in favor of more hyper-competitive, fast turnaround time conferences. So do you think this relatively new publication system is appropriate? Are there benefits or not benefits, or is there something that you would like to see being done differently?
All right, I'm going to say a few things. So I'm going to shamelessly promote a recent paper I posted. It's called An Open Review of Open Review, where we— I
honestly did not know about this, but I'm so happy you're saying this.
Okay, well, yeah, so I have my REU team worked on this project over the summer. We scraped a whole bunch of web data. We scraped data from Open Review. We scraped data from other sources like archive citations, semantic scholar data. We took a bunch of data from CS rankings, and we just looked at a bunch of issues in the review process. And one of the things that I thought, one of the things we looked at pretty closely is how archive affects the review process. And there's one particular thing that came out of that struck me as this is an issue that I really wanted to look at. Is recently a lot of conferences have been trying to sort of discourage. We want to have low acceptance rates, but we also want to discourage resubmissions. It's sort of the idea that the papers that are rejected, we don't want to be reviewing them over and over again. And so one of the things we looked at is papers that have been rejected from another conference. And we don't know exactly where things are submitted, but what we did is we said, okay, let's assume that things have been online on archive for 3 months before the conference submission date. They've almost certainly been submitted to another conference. And I think that that's a pretty reasonable assessment. And you can even look further back than that, right? So things that have presumably been submitted to another and rejected from another conference, do they review better or worse than first-time submission papers? And going into this, I just assumed that they would review worse. I didn't know if that would be a strong effect or if that would be a weak effect. I had no idea. But the shocking thing is that papers that were rejected from another conference reviewed better at iClear than papers that were first-time submissions. But what that says to me is that another thing we looked at is what is the correlation between the reviewer scores and the citations that a paper gets. You might think that really high impact papers, impact measured by citations, you can argue about how good of a measure that is, but it's one of the only, scientifically definable measures we can grab, right? Those correlations are almost zero. We find that papers that get better scores actually do tend to get more citations, but that's only because they're accepted to the conference. And when they get into the conference, they get more publicity. But if you break it down by groups and you say, okay, among papers that appeared at the conference, is there a correlation between citations and reviewer scores? The correlation is almost zero, right? And what that says to me is that there's a lot of subjectivity in the review process. I don't think it's that the review process is random per se. I just think it's that the review process is incredibly subjective. And when you look at the fact that we're rejecting 80% of the papers from some of these conferences, but then the papers that are recycled and resubmitted, they don't review any worse than first-time submissions. To me, it says that our acceptance rates have just gotten too low. And when you set the acceptance rate that low, I think it's just inherently true. When the number of papers you're going to accept is less than the number of papers with merit, it becomes incredibly subjective what papers you're going to accept. And I think that we've sort of gotten ourselves into a regime of very high subjectivity.
Why did you expect that the reviews would go down?
So there's different interpretations of this, right? You would think that papers that were rejected from another conference might be in some sense, statistically worse than papers that have not been rejected from any conference, right?
No.
You don't think so?
I mean, if the review process is random, that's not true.
Sure, it's not true if the review process is random. It's also not true, it's also not true if people are actually making revisions to their papers based on the reviews, or maybe just based on time, right? Like you always kind of rush to get your papers to the deadline and you get them there, but you can clean things up afterwards.
Really what happens is the following. There is an assignment of papers to reviewers that is based on an algorithm.
Yep.
And the algorithm has a lot of potentially noisy inputs and constraints that might lead to things such as, case number one, the reviewers, the 3 reviewers that happen to be assigned are really excellent reviewers and a very good fit for the topic. In which case, the outcome, more likely than not, will be what you were expecting, that if the paper was accepted, then it was a good paper, and otherwise not. But in a good number of cases, the reviewers are not ideally assigned to that paper. And so what happens is that either you are not overly negative because you don't quite understand the paper, and so these papers all end up in the borderline zone, and therefore it's really a random process as to which one gets accepted or which one gets rejected. And therefore, if you get rejected and you go to the next conference, it could be the case in a good percentage of papers that they are transferred from these not ideal reviewer group to a better reviewer group, and then they become accepted. But it can also go the other way around, because if you go from the middle, from reviewers that were not ideal, then the weaknesses of the paper could be revealed in the next round. So I think it's a lot more complex than just assuming that because you got rejected, the paper was not good, or vice versa.
I'm not sure I agree, though, that there is, quote, a good and a bad set of reviewers. I think there's just a lot of subjectivity, right? Like I've had reviewers for papers of my own that I completely disagreed with the reviews that they gave. Sometimes I've had really good reviews that I thought I disagreed with the things that they said. And sometimes I've had bad reviews when I really disagree with the things that they say. But it's, that doesn't mean that the reviewers aren't experts, right? It just means that their opinions are very different than my own. And in fact, sometimes I can tell that they seem to have a lot of expertise. And they can point out very specific related papers that you might only be aware of if you really were in that field. And yet I still get comments and opinions from them that I'm quite surprised by. But I would agree that there is a lot of randomness. One of the things we actually did, interestingly, is we did some Monte Carlo simulations where you sort of use the variance between reviewer scores to estimate how reproducible reviews, accept or reject decisions are. And our simulation seems to indicate that accept or reject decisions might be as high as about 75% reproducible at a conference like iClear. But I think that, like you said, that things like the Toronto paper matching system, depending on which conference you submit to, there's going to be huge variations in the reviewers you get matched to, depending on what sort of populations there are at different conferences and how that interacts with the paper matching system. And so you get huge swings submitting from conference to conference, right? Yeah, but whether or not there are a set of good reviewers, or whether expert reviewers are really, whether their opinions are necessarily better, I don't know. I'm not sure that I agree that they are. I think there's still, beauty is still sort of in the eye of the beholder, and there's just so much.
My personal guess, so I've not done the formal statistics, but being the oldest panelist, I've been area chair a very large number of times. And so every time is 30 papers times 3, so it's 90 reviews, and probably 3 times a year, doing that for many years. I'd say a good 50% of all the reviews I've handled as area chair just were not adequate. A lot of them are just incredibly short. And it may change also depending on the field, but in computer vision in particular, the comments of it didn't cite this paper that appeared 2-3 months ago that did another 1% better than what is published in this paper, are just so common and sometimes so infuriating, because first of all, reviewers are not supposed to ask authors to compare to papers that have not been published. And so therefore, this idea that you have to do 2 or 3% better than a paper that sometimes appear in archive after the conference deadline, that I think it's really, it's getting to a lot of those extreme situations that are, you know, how can you expect authors to compare to everything under the earth? That's just not the way it should be. And so I find in computer vision, at least, more than 50% of the reviews to have those kinds of requests.
So perhaps commenting on that and what Tom was mentioning before. So Tom, actually, if you had asked me what I thought, how papers that were resubmitted, you know, would they score, you know, on average higher or lower? I would bet that they would score higher, precisely because I was counting on papers using the feedback to improve on these papers. And that's actually one of the points that I was trying to get to, which is when there is a deadline for everybody, for authors, but also for area chairs to take a decision on a paper, then this conversation about what should be improved in order to improve the quality of the paper, what are really the concerns, what are acceptable concerns and what are not acceptable concerns, that conversation oftentimes gets demoted. And so that is a conversation that I believe still exists in other slower means of publications like journals. So for instance, for the panelists in your groups, do you try to keep a balance between journals and conferences? Do you think that balance should be dependent on the stage of the researchers? Do you think, do you have any strong opinions on that, on what that balance should be?
I can add a little bit on the conversation from a more theoretician perspective. I guess this really depends on what you do. Honestly, I think journals fare better with theoreticians just because I feel the reviewers sometimes read the proof more than the conference reviewers who really actually read the proof at all. Often they just judge the paper just on its face value. Sometimes they don't even read carefully about the assumptions and they don't really understand the theory. But journals, you typically have much more time to really digest the results. So I feel and the feedbacks are typically more constructive. But on the other end, students these days, they want to get papers in this, high selective conferences so that they look nicer to the future employees. They get jobs, they get job offers much easier. So it's a trade-off. Still, I think right now these days, I still do more journals than conferences. And I wonder if, there's maybe two ways to go down the road. One is to do something like split this huge conference like SML, NeurIPS to a smaller subtracks of conference, which each of those are more focused on different disciplines. So we can all read more high quality work, just more closer to our own focus. The other possibility is maybe to do something like a rotation deadline. I start to see some of this in some other communities such as Sigmatrix. They do this rotation deadline, so you actually have a little bit of memory in terms of the review of this particular paper. Maybe it got first rejected, but there's a lot of, so it's somewhat like a journal. You get some feedback, you can do a second round of submission, but then still you get to advertise your work at a top conference in the field. So maybe that's also an opportunity that just maybe everyone can write less paper. I think the issue with a really low acceptance rate, then people are forced to write more papers, and then everyone are forced to review more papers, and then the acceptance rate is getting lower, and we send going down the rabbit hole, which is not really good for anyone.
Yeah, I like to send papers to conferences just because. So one of the things we found in our study, papers that, like I said, papers that don't get into the conference get way fewer citations of papers that then get into the conference. And if you look at papers that get into the conference, there's almost no correlation between reviewer scores and citations. It just seems like getting into the conference boosts your citation rate. And I think the reason for that is you have a poster at the conference and you put it up in one of these big rooms and you might have 200 people that come by and see it, right? And I think one of the difficult things with journals is just that people don't really read journals anymore. If people read your paper, it's because they saw it on archive, right? And it was discussed online.
Yeah, right. Well, most of these classical fields for this journal, the classic, they traditionally have lower citations, right, than this new ribs or CMO in general.
Yeah,
But that doesn't really mean these works are of less value if you
Yeah,
also think about other factors in terms of impact.
Yeah, there's huge limitations to using citations to measure impact, and I totally acknowledge that. And I think one of the problems is that there are fields like experimental computer vision where citation rates are huge, and you can do amazing work in theory, and the citation rates are just lower, right? So it's a flawed measure of impact for sure. But I think it's kind of nice to have somewhere to put your paper in front of people where people will actually see it, because otherwise there's just so many papers coming out every week that it's so easy to get lost in the noise.
Yeah, I definitely agree on that. I mean, even for our own papers that are published in this, higher level conferences tend to get more citation and more attention just because it has its brand and people just tend to read those papers more seriously than the others.
Yeah. But because of that, I think conferences are really healthy academic communities, right? The conference itself is an opportunity for people to exchange ideas and see what everybody's working on. And it's very difficult when there's thousands of papers popping up to be tracking archive all the time. But when everyone has like a dedicated week where we're all going to walk around in a room and look at what everybody's doing and speak to each other, I think it makes for a very healthy academic community. Now the review process to get there, not so healthy, right? But I think the actual conference process is a really good, healthy thing for the community, which is why I prefer to submit things to conferences.
And that is precisely what I guess we're trying to do now virtually by means of this by this workshop.
Yeah, I gotta say this workshop is incredibly successful. I think you got a great roster of attendees. But one of the things I'm worried about with COVID is I think that a lot of these big conferences we've just sort of lost the synergy that happens, and I think a lot of this the benefits that the community gets from these conferences are just not happening right now. Right, it's just difficult to get the attention span to go to like a week-long, conference and.
Yeah, what I really miss is those coffee breaks. And now the coffee break is just a lonely trip to the kitchen.
Right.
Okay, so I just want to take the opportunity to thank everybody. And again, if there are any other comments or questions from the audience that you want to raise, this is your opportunity. Otherwise, this will conclude the first day of the workshop. And again, thank you so much to all of the panelists for your opinions. And this has really been some interesting discussion. I would push back, Tom, on that observation that no one reads journals anymore. I have a pile of journals right next to me right now that I need to get to. But
how big that pile has gotten before you get a chance to read it, though?
It's growing, but
that's an exaggeration. I shouldn't say nobody. Even I, when a journal comes out, sometimes I'll peruse it and see what's in there, and I'll pick out a paper to read.
I do feel it's much harder to get reviewers for journals these days, given I'm a social editor. Now everyone is reviewing for these conferences. Nobody's reviewing for journals.
Okay, so with that, let me then thank one last time to all the panelists and all of the attendees. This has been really, really insightful, and looking forward to seeing everybody tomorrow for the second day of the workshop. Even more interesting, we'll have more of the interesting talks that we've been having today. So good afternoon, everybody, and see you tomorrow.
Bye.
Bye, thank you.